Hello, this is David Holliday, and I'm going to introduce you to some search algorithms today that are used in computer science. These are going to be methods for searching data sets. The two that we'll be looking at are called the binary search and the depth first search, also known as the DFS. Now, the binary search is primarily used to search through arrays. It's going to scour an array for a target number, but it has to be used in a sorted search pool. So the arrays must be in either ascending or descending order. The search begins in the middle of the pool and compares the value at that location to the target value. And then depending on what that comparison produces as far as results, it's going to start a process. So until the target is found, the search will continue by either checking the middle of the higher remaining half of the search pool or the lower half, depending on how the target value compared in the previous step. So to kind of illustrate this for you, I've got an array. That's what these boxes represent. Let's say our target number is 35, our target value. We're going to fill in some values into these index spots, and we'll perform our first check. So the binary search starts in the middle, identifying the middle index, which in this case contains the value of 26. The number in that index is compared to our target. It recognizes that 35 is greater than 26, which means because this array is listed in ascending order, the target must be on the upper half of the array. So now it isolates just the upper half from that middle index that was identified on all the way up to the end. It's going to just check these index positions. So we'll isolate those in our illustration. We'll fill them with the appropriate values. We'll perform our second check. Now, what does this search do if there is an even number of indices remaining? It can't find an exact middle. You see there is no middle index here, so it will prefer the lower. So it'll find what would be the middle, and then it will round down, so to speak. So it's going to start here at this index. It's going to recognize that that number 30 is less than 35, so it's going to say, our target must be in the upper remaining half. So then it isolates the remaining index positions. We'll fill those with our values and perform the third check. Once again, the middle would have been here, but it rounds down, so to speak, and we find ourselves at the value of 35, which is our target. And so we were able to find the value we sought with just 3 comparisons required. One in the middle of this search, the second in the middle of this search, and the third here. So hopefully that makes sense. And to kind of switch things up on you a little bit, we move into the depth first search, which covers a fairly different type of search. It's not just comparing values within an array. This is more of a traversal algorithm. It tries to work its way through data sets that are a little more varying, perhaps I could say. It can be used on graphs. It can be used on data trees. They can be sorted or unsorted. And it really just kind of crawls its way through the different nodes, searching for the value that it seeks. So this algorithm starts, in this case, at the starting node at the very beginning and follows a pathway to the end of the branch. It'll isolate an entire branch, go from beginning all the way to end, and once it has exhausted that branch, it backtracks and finds a new branch to search. So to give you an example, we will search for the target number 6. I am not going to fill in all the numbers of this tree for the sake of helping you see how the algorithm navigates it. But we'll start at the root node, and we will do our first check, and we find the number 1 in this node. we recognize that is not the correct number. So it will continue its way down a branch. We're going to illustrate using this far left branch. So you'll notice that the second check would happen at this node, and we find the number 8. Again, not the correct target value. So it will continue its way down this branch all the way to the end, where it will perform its third check, and it finds the number 2, also not the target number. So now it has to backtrack, and it will work its way back up the branch until it gets to a pathway it has not checked, which in this case is this second child node. So the fourth check is going to take place here, which produces the value of 7, not our search target. So it's going to backtrack again. There are no other pathways to take in this branch, so it backtracks another level. There are no pathways to take here, backtracks to the first level again, and begins its way down the next branch. So we check this node, we find the number 4, we check the bottom of this branch, and we find the value 6, which is what we were searching for, and this search is complete. It required 6 comparisons in this example, and the efficiency of this search is largely contingent on the number of nodes and edges that are present in the data set that you're searching through, that you're traversing. So just to compare some of the qualities of these two different types of searches, you'll see that these algorithms have some similarities. When it comes to function, DFS and binary searches both have to make choices between pathway options, whereas the binary search is choosing the upper or lower half of an array, and the DFS is choosing which branch it wants to traverse based on what has been covered so far. They also both isolate portions of the data from the whole so that they can search through that portion rather than considering the entirety all at once. As far as efficiency goes, they're both contingent on the size of the data structure and the location of the target contained in that data structure. So if the binary search has a large number of index values, it will take more comparisons to finish the search, which means it will take longer to search. If there are more nodes and edges in the tree or graph that you're searching with a DFS, it's going to take longer to search all of those positions to be able to see if that target is contained in that data set. And then finally, as far as use and application, they can be used to find a single value. That's a similarity that they have. If you're searching for a single value, they can also both be used with recursion. So recursively, they can call the next step. And then at the same time, they have these similarities. There are just so many significant differences because they're largely applied to very different types of data sets. And so while we are on the topic of differences, we'll take a look at some of those as we contrast these two algorithms. When it comes to a depth-first search, the functionality of it is going to be in its use. It is used on sorted and unsorted trees and graphs. What it does is traverse node structures from node to node, identifying appropriate pathways to take. And then the function of the binary search is that it's used on arrays. So as I mentioned, the data structures are different, which means their operations are quite different. The data in the binary search must be sorted, as I've mentioned before, and this performs direct searches primarily. And this one is most focused on the traversal. They both search for a certain number, but a certain value, but in this case, this is more focused on the pathway. Efficiency-wise, we see that in the Big O notation, the efficiency of the depth-first search has to take into consideration the number of vertices and edges. That's what the V plus E represents. So the more nodes that are present, the more connections between those nodes, the longer it's going to take for this algorithm to navigate those pathways. Whereas in the binary search, we've got a consideration log of n, where the length of the element list dictates how long the search takes. While it does cut in half with each comparison, which improves things compared to just a straight big O of n, for example, where the number of indices is how long it will take. This is going to cut in half each time, and so that amount is going to change with each step. When it comes down to uses and applications, the DFS is useful in searches where those connections matter. So if we're trying to identify a pathway, whether it's solving a maze, for example, or if it's in this specific example of GPS application, where we need to find the fastest route, or maybe we need to find a certain location amongst a chain of routes, a series of locations. It can also be used for cycle detection. Now, in the case of the binary search, it's useful for large data sets or in instances where we need to search multiple things in the same search pool, so that we don't have to search the pool one thing at a time. This is very helpful when you're doing things like finding a customer's name in a database that has millions of customers, because of all that data. We don't want to do a one-to-one-to-one-to-one type search where we iterate one index at a time, but the ability to cut the array in half and move forward saves quite a few comparisons and improves efficiency. Hopefully all these things make sense a little bit more. Appreciate you watching, and if you have more questions, I'm sure the internet has much more information for you, but thank you for your time.